In this video, I'll be discussing the effective nuclear charge and periodic trends. You'll want to watch part 1 of this video, which reviews the effective nuclear charge, before continuing. We'll continue our discussion by talking about 2 additional periodic trends. One is the ionization energy, specifically the first ionization energy, and the other is metallic character. As with the previous trends we discussed, atomic size and electron affinity, we're interested not only in what these trends are, but why they arise. Let's look at some data pertaining to the first ionization energy. This is defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. We're looking at a plot here of the first ionization energy as a function of atomic number. You'll notice helium, neon, argon, and krypton are present for these spikes in the first ionization energy. This means that noble gases generally have high first ionization energies, meaning it takes a substantial quantity of energy to remove 1 electron from a mole of gaseous atoms. Now, species that have lower first ionization energies are shown here. These are lithium, sodium, potassium, and rubidium, which are labeled. And these species are alkali metals. What we can interpret here is that for the alkali metals, it takes less energy to remove 1 mole of electrons from 1 mole of gaseous atoms than it does for noble gases. We can also observe some general trends. As we move from the alkali metal to the noble gas, so moving from left to right, from lithium to neon, we can observe a general increase in first ionization energy, meaning it requires more and more energy to remove a mole of electrons from a mole of gaseous atoms for species that are closer, as in further to the right on the periodic table. Now, this is simply a trend. You will notice some deviations from this trend are observed when considering atomic numbers from lithium to neon, as well as from sodium to argon. What we're focusing on here is the general reason for the trend, and we'll talk about exceptions to the trend when we get more into electron configurations and those types of considerations. So let's look at a plot showing, and this is the color-coded periodic table where darker values correspond to higher first ionization energies and lighter values correspond to lower first ionization energies. Generally speaking, you can see that the first ionization energy as a trend increases when moving from left to right, as well as it increases from moving from the bottom of a column of the periodic table to the top. So again, let's focus on why this trend exists. Let's first talk about why the first ionization increases moving from the left to the right. So what we observe is that the effective nuclear charge moving from the left-hand side to the right of a particular row of the periodic table, as we move from left to right, we know from the previous video that the effective nuclear charge increases. And we also know that that means the atomic radius or atomic size decreases. The electron cloud is held more tightly closer to the nucleus. What that means is it takes more energy to remove a mole of electrons from that mole of gaseous atoms because the electrons are held more tightly. And again, to summarize, the reason for this is because atoms on the left or on the right-hand side of a particular row of the periodic table have a higher effective nuclear charge. So again, for noble gases, we tended if we were looking on an individual row basis, we observed in the data set that noble gases tended to have the greatest first ionization energy of all of the elements in that row. And again, that's because they are the smallest in size, which means the electron cloud is held more tightly to the nucleus. And this means it takes more energy to remove electrons from those atoms. Now let's look at what happens as we move from the bottom of a given row on the column on the periodic table to the top of that column on the periodic table. Now what happens here, and we know from the previous video that atoms toward the bottom of a given column are larger than atoms on the top. And this is because their electrons reside farther from the nucleus. What this means in terms of ionization energy is that those electrons, because they reside in orbitals generally farther from the nucleus, means that they're easier to remove, so they take less energy. So when we look at francium down here, this is a very large atom. Its valence electrons are in 7s orbitals, and it is relatively easy to remove these electrons, therefore requiring relatively low energy. Now, when we look at lithium, its valence electron is held in a 2s orbital, which means that it has a higher probability of being found closer to the nucleus. It's more attracted to the nucleus, so therefore it requires more energy to remove this electron. So again, we can explain these trends for the same exact reason that we used, or the same reasoning that we used when talking about atomic size, which is based on arguments surrounding effective nuclear charge and the principal quantum number n associated with the valence electrons for a particular element. Let's compare the successive ionization energies of two different elements. On the left in purple, sodium, and on the right in blue, magnesium. Now, if the first ionization energy is the energy required to remove one electron from 1 mole of gaseous atoms, the second is the ionization energy required to remove another electron, and the third, the next electron, etc. So as we go up this staircase, so to speak, removing the first electron from a neutral sodium atom results in a sodium plus cation. Removing an additional electron results in a sodium 2 plus cation, and removing a third electron results in a sodium 3 plus cation. Now, when considering the electron configuration of sodium, you'll recall that it has one valence electron in the 3s orbital. The first ionization energy for sodium is relatively low, meaning it's relatively easy, energetically speaking, to remove this electron. However, when comparing the first and second ionization energy, you can see that the second ionization energy is significantly larger, and that's because the electron would be removed from the sodium ion with an electron configuration pertaining to helium. What that means is that those electrons experience a much higher effective nuclear charge than this 3s electron did, and that's why it requires a substantial quantity of energy to remove it. Now let's contrast that with magnesium, which has 2 valence electrons. Again, the ionization energy associated with removing the first electron is 738 kilojoules per mole. There's not as big of a step for the magnesium between the first and second ionization energy as there is for sodium. And this is because removing the first electron takes it out of the 3s shell, or 3s orbital, and then removing the second electron is removing that second electron out of the 3s orbital. Now you'll see that the third ionization energy, however, between the second and third, there's another large jump in energy. And this is because now we would be removing one of the electrons that was previously in the core. Okay, we're removing one of these core electrons, which again experiences a high effective nuclear charge and therefore takes a substantial quantity of energy to remove. Let's now consider metallic character. Think back to when we compared properties of metals and nonmetals. Metals were substances that were solids at room temperature, malleable, typically conductive. Sometimes you hear shiny as a description, okay? And most of the periodic table is composed of metals. But we can actually rank elements in terms of their metallic character, which is how much they resemble, or how much their properties resemble that of metals. Now, you'll also remember from previous modules that metals tend to form stable cations, and that's very important for why this trend is observed. So what we see as the trend is that the metallic character tends to increase when moving down a column, as shown on the right, and it tends to decrease when moving from left to right across a row of, again, these are main group elements. So we can see that toward the bottom and on the right-hand side of the periodic table, the at least visual representations of the elements much more closely resemble those of what we would think of when we think of metals. So let's first talk about when moving down a column trend, we see that metallic character increases. And this is because the ionization energy decreases. What this means is it's easier to remove electrons from species lower down on the periodic table, and this is because those electrons are less tightly held than in the case of smaller atoms. And of course, I'm kind of combining trends here, right? We've talked about size, we've talked about ionization energy. These trends are interrelated for sure. So when we move down the periodic table, a particular column, we see that ionization energy decreases, and therefore metallic character increases. So as we move from left to right, we see that metallic character decreases, and the reason for that is because we actually see an increase in ionization energy as we move from left to right within a row. What this means is that species farther to the right of a particular row require substantially more energy to remove their outermost electrons, so thus they're much less likely to form stable cations. So again, to summarize, as we move down a column, the metallic character increases, and the reason for this is because the ionization energy decreases, connected to the trend we just talked about, and as we move from the left to the right of a row, the metallic character decreases, and the reason for this is because the ionization energy increases. So you can think of them as being the opposite of one another. So in this video, we've discussed ionization energy as well as metallic character, both the trends and why they arise. Consider working on this bonus practice problem where you're given a set of four successive ionization energies: the first ionization energy, second, third, and fourth. And you're asked to come up with or to generate which third period element these ionization energies belong to. Good luck with that, and I'll see you in the next video.